Well, welcome to this online session for making good round-baled silage. Let's talk about a few pros and cons about making baleage in the first place. We are certainly in need of the options that baleage gives us to avoid rain damage for making stored feed, and it allows us much more timely cutting. And an advantage I don't list here is that it is fairly simple to do, and there are there's more access to wrappers than there has been in past years. On the disadvantage side, there is a need for heavier equipment and also access to those wrappers, and it is very hard to determine moisture content in the moment, and we'll talk more about what that means a little later. There is expense and labor involved. We still have no real good solutions for what to do with the plastic when you are done feeding. And then there is the potential for animal feeding issues and even death, although by the time we finish this presentation tonight, I hope to make you much more comfortable that you can make baleage without or with a great deal of assurance that you're not going to have feeding issues. So it's important for us to know what good baleage is. Good baleage is going to have a moisture content between 40 and 60%, and more than likely, or the research is showing us that we would like it to be 50 to 60% on the wetter side of that range. We want to have tight uniform bales. We want to have 6 layers of plastic or more. And in years past, we have actually had materials printed and research that shows 4 layers is adequate, but it gives you no insurance against stems poking through plastic and other things that might cause holes. So the good producers of baleage are using 6 layers of plastic or more. We also know that to make good baleage, we have to cut early so that there are more water-soluble carbohydrates, and these, of course, are the energy that fuels fermentation, and that faster fermentation causes a pH drop. And that pH being low, below 5, is what gives us stable silage. Fermentation makes lactic acid, or at least good fermentation makes lactic acid, and we want levels at 3% or above. And we don't want butyric acid, so we want butyric acid at 0.1% or less. And butyric acid, as we'll hear more about a little later, is a marker for poorly fermented baleage. We want the percent of nitrogen as ammonia to be less than 15%, and we'll talk about why. We also want the ash content, which is the minerals in the forage, to be 8 to 10% or less than 11 or so. Of course, you can make good baleage with inline or individual wrappers, and they have different advantages. Inline being a little faster, uses less plastic. Although you've got all of the bales in one site, once you bale them and wrap them, they're going to be there until you have to move them to feed. The individual wrap bales have got a lot of plastic on the flat sides that can lend itself to some insurance when you set it on the ground that you're not going to have holes. You can also probably do it with a little less labor, and you can move the bales from the side of baling to the side of feeding at any time you want, and one at a time. Now, what does low pH and high lactic acid mean in the first place? Well, the biggest thing it means is that forage is stable in storage, and that forage will have a good bunk life when it's fed out. It also means there's a low probability of having any sort of clostridial bacterial infection or the toxins that come from it, and a low probability of listeriosis, which is also a problem of off-type silage, usually from rotten silage that has been exposed back to air. Now, there are many good reasons to make baleage, and we certainly recommend that to make it if you can, but the biggest barrier that I'd like to address, among other things today, to making baleage is this: the fear of botulism. So to this end, we actually, over the course of the last 3 years, 2017, 2018, 2019, conducted a project to take a deeper dive into what constitutes good baleage. So the purpose of it was to define the quality of our Kentucky baleage, especially pH and volatile fatty acid profile, and that we abbreviate that volatile fatty acid as VFA, and those are the lactic acid, acetic acid, propionic acid that we want, and of course we'd like to know about the butyric acid content that we don't want. All of those are volatile fatty acids. And we would like to identify the practices that lead to low pH and especially that good VFA profile. We took forage tests from 2017 to 2019, and in 2019 we did a much more in-depth look at what the farmer practices were that to associate with the baleage quality. And another major purpose is to develop confidence in the quality and safety of haylage or baleage for livestock consumption, including identifying the risk factors for bad or possibly toxic silage. So here's what we did. We located and sampled a diverse set of bales and analyzed them for moisture content, nutritive value, crude protein, TDN, relative feed value, the usual things, and the volatile fatty acid profile, with a special attention on lactic acid and butyric acid. And I do want to thank Brandon Sears, Corinne Belton, Levi Berg, April Wilhoit, Tommy Yankee, Don Sorrell, Dr. Jeff Limcooler, and Dr. Michelle Arnold for their help with this project. We took samples from 6 counties in central and northern Kentucky over 3 years. These samples had a wide range of forage types from small grains, regular grass, summer annuals, and legume grass. We had 44 samples from 2017 and 2018 and 50 from 2019, and all were analyzed at a certified commercial laboratory. Here's what we found. We found that the forage quality was good. Let's take a look at this table and see what's present in it. On the left are the types of forages that we measured. This is 2017-2018 data. Small grains, grasses, summer annuals, and legume grasses, and the number of samples. Here's the moisture content that we found on average across all of those. And you'll notice a couple of things. The small grains and the summer annuals had moisture contents outside of what we would call our optimal range of 40 to 60, actually quite high. The grass and the legume grass were right dead smack in the middle of that range. Looking at crude protein, the next column over, the numbers that you see there are actually high for the types of forages that we're showing in this table. Lactic acid numbers were in general pretty good, actually 3.2 for small grains, 3.2 for summer annuals, a little lower for grasses and legume grasses. TDN was good, relative feed value was good, and the pH numbers were actually acceptable, even though we'll talk about this pH 5.5 and what that means in just a little bit. But we'd like to have pHs at 5 or below. These are at right on the tip of the range there. This certainly is a good pH average for the small grains. So forage quality and fermentation quality was as a whole awfully good. Here is a key finding that we'll talk about throughout the rest of the presentation, and that is that moisture content was the biggest factor in lactic acid content. So in other words, if we know the moisture content, then we're halfway home to getting good lactic acid generated in the bales. And I want to draw some lines here to help make sense of this graph. Obviously, moisture content along the horizontal axis, lactic acid is on the vertical axis. Here's the lower end of that moisture content we want for baleage, 40%. And there's the upper end, 60%. And we want 3% lactic acid. And so there's that line going across the graph. One thing you'll notice very quickly is that in other words, we want to have points or samples that show up above the horizontal bar and between the two verticals. And we only have one that showed up there with more than 3% lactic acid. We got a lot that showed up with the right moisture content between 40 and 60, but that had lower lactic acid contents. We had a lot above the 60% range, and this was where we began to pick up a lot of lactic acid. So now this is, you might say, oh my gosh, this is disturbing, we can't make baleage. Well, that's not true. We've known this for some time, that when you're looking at baleage as a silage system versus chop silage that we think of with things like corn silage, it is much more difficult to get high lactic acid concentrations in baleage. It's something that we have known, but it is, so I guess this is normal, what we're showing you right here. And again, this is just 2018 numbers. 2019 is going to be similar. The other VFA, volatile fatty acid, we have concerns about, of course, is butyric acid. This is also that 2017, 2018 data, and we only had one sample that was really excessively high in butyric acid. We had several that were above the 0.1% level in this cluster of points here, but again, all of these moisture contents were 70% or above. Below 70%, which is again outside of the recommended range. So between 60 and 70, we had a lot of good silage produced, good baleage produced. I'd like to switch gears now and look at just the 2019 results. This is a little more complex graph because I've added the pH, which is the blue dots, and there's a little dashed line that helps you follow the trend there for pH. The green dots are going to be the lactic acid concentrations. And again, moisture content is the horizontal axis. pH or lactic acid is the vertical axis. So these are the 2019 samples. We draw those same guidelines on here. We also see a similar effect, that we only have a few samples that fell above the 3% level in this desired range of moistures from 40 to 60%. We again had samples drier and wetter than 40 or 60%, and those above 60% did tend to have higher moisture contents. Now we'll pay attention here in just a second at these 3 or 4 points over here on the right-hand side, particularly these 3 that wound up being very wet baleage samples with low lactic acid numbers. First, I'd like to ask the question, is low moisture a problem in baleage? Because you can see there are quite a few samples that are down on the lower end of the range. Well, here's what we know. First of all, low moisture baleage, we call that less than 50% moisture, does not ferment well. That's what we've known for some time. It will have low lactic acid content. We've known that too, and our samples certainly bear that out. The pH values will be above 5. Now let's flip back a couple of slides and look at those pH values for those drier baleage samples. And if you look at baleage above 50% or 50% moisture or less, in other words, drier than 50-50, you can see that the pHs started at about 5.5 and went up to about 6. So yes, our dry baleage didn't have much lactic acid and had pHs above 5. The recent research, though, on this type of baleage tells us a lot of very positive things, or certainly things that make us feel better. Dry baleage does preserve well, and it stays stable long enough to feed out if anaerobic conditions are achieved and maintained. And that means 6 layers of plastic, and it means that you make sure that the plastic stays whole. In other words, tape holes that happen in bales. Where we have had some of our worst feeding experiences, they've come from very wet lots of baleage, but where we've had some really bad holes in inline wrap such that the bales only partially fermented and then went through a secondary clostridial fermentation, and in fact we've had botulism happen in that particular case. So low moisture baleage is nothing to worry about if it's wrapped well and kept anaerobic. If you take a look at the moisture content on butyric acid, and this is the 2019 Baleage, you can see the same effect. Butyric acid was basically 0 all the way up to 60%, with the exception of maybe one bale. And above 60, then we began to pick up more and more butyric acid. And there are these, I told you about the samples on the right-hand side of the graph. Those that had low lactic acid wind up having pretty high butyric acid. And that's a concern, and we'll tell you why in just a moment. So, this is leading to the next point, and that is, does high butyric acid mean botulism? So we know butyric acid is the marker for bad fermentation, and as I'll show you, butyric acid is produced from clostridial fermentation, but does that mean botulism? So first of all, let's talk about those conditions leading to clostridial growth. The first one, and the major one, is very high moisture content, above 70% usually. Anaerobic conditions. Clostridial bacteria is an anaerobic bacteria. Poor fermentation, which means you've got low carbohydrates in the forage. It means it's probably mature when cut, such that the pH drop is low. Now, I didn't really go into this, but the fermentation process of Baleage is a multi-step process. That first starts out with acetic acid bacteria that starts the pH drop. It then leads to the growth of lactic acid bacteria. But if we're wet enough, and if then we can have what we call a secondary fermentation by clostridial bacteria that then will take the fermentation to steps or to products that are undesirable. Clostridial fermentation is also made worse by the contamination of forage by soil. And of course, we measure that in forages. That's the ash measurement in our forage analyses, from manure and from dead animals. So that's the source of clostridial bacteria on our forages, because fresh forage, uncontaminated with soil, manure, or dead animals, is low in botulism or clostridial, low in clostridial organisms. So let's talk about, or make some, clarify that relationship between clostridial fermentation and botulism. First of all, there are several Clostridium species. And I've already said soil and manure are the most common sources of contamination of forage. Botulism comes from the toxin produced from one particular species, the Clostridium botulinum bacteria. And our best indicator for clostridial fermentation is butyric acid content. Another indicator is the percent of crude protein as ammonia, because Clostridia break down forage protein and release ammonia. So if we have high levels of ammonia, above 15%, and we'll reiterate that at the end of this presentation, we have high levels of ammonia, it's an indicator that we've had clostridial fermentation. But remember that butyric acid or clostridial fermentation is not the same, and it does not equal botulism. Let's take a look at dirt in Baleage, or that ash content, where ash is the indicator of the dirt in Baleage, or the contamination with soil. The normal is about 6 to 8%. Above 11%, it indicates dirt contamination. The most common scenarios for high ash content: a lot of rain damage or splashing of dirt onto forage as it's laying in the windrow or in the swath. Extremely dry conditions when raking and baling, and this is the condition or a scenario like this is where we've had the very highest ash contents I've seen in baleage ever, close to, at 25% of the bale weight or greater. Another place it can come is from aggressive raking of a heavy crop, and especially this is true where we've got drilled forages with bare dirt between the rows. We see this most often with small grains, but it happens also with summer annuals because these are most often planted in rows and you'll have bare dirt between the plants. Now, all that being said, I want to change gears here and focus on that moisture content dimension of baleage because it is so important to the end product. This is the 2019 data, but in this case, this is the moisture range on the horizontal axis and the number of samples on the vertical, less than 40, 41 to 50, 51 to 60, 61 to 70, and above 71%. And what you can see that there are more samples outside the desired range, 40 to 60, than within it. If you add 12 and 14, that's 26 and 30 versus 27 inside the proper range. So it just says that moisture content is really hard to hit time in or to get correct. We've got both dry and wet conditions. So let's talk about how we might measure moisture content. These methods are also outlined in our Baleage FAQ publication that is on our UKY Forages website. If you Google UKY Forages and look at hay or haylage, you can find it. Or if you just Google Baleage FAQs, UKY, you'll find that publication. So I'm going to go through these and elaborate a little bit. But the one way is to use what we call the dish rag test. And if you take a handful of forage and wring it out as if you would wring out a dish rag, and if moisture content can be expressed from the forage, in other words, squeezed from it, it is generally above that 65% moisture range. You can also use a Coster type forced air dryer, and that's it on the right, where you would get fresh forage from the windrow, you'd chop it up, you'd put it in the basket, you'd place it, you get a fresh weight, place it on the forced air heater here, and dry it until it's at a stable weight, and then make your calculations to determine the moisture content. That's a slow method, and obviously you can only do a very small portion of the forage in the field at one given time, but it certainly is an accurate way to measure moisture. The other one is the microwave method, which you can do similarly. You would put forage in a paper bag, you would weigh it fresh, you would put it in a microwave, and you would use intermittent applications of power, most of the time less than full power, until it is dry and reaches a stable weight, and use that as your method to determine moisture. Both of those, of course, are slow and not really conducive to field operations, but it is a way for you to get a feel for moisture content on silage. There are commercial moisture testers, and I'd like to talk about a couple. The one that you're seeing the picture of on the right is a windrow tester made by the Agritronics people, and I'm not giving you a commercial for them, but it was a windrow moisture tester I could find quickly for a picture. And you use a system a lot like that with the one on the right with a 5-gallon bucket, try to put a fixed amount of forage in there, press down, take a measurement, and the scale on the bottom is so you know how much pressure to make pushing down on that probe. Historically, and we haven't done tests with this particular probe, but historically windrow tests are extremely variable and typically are, well, just variable and lead you to maybe incorrect conclusions, but certainly you get a wide range of results. There are bale probes after you've made the bale, and Agritronics, again, is one brand. There are several that are out there. In fact, it seems that most of the major manufacturers of balers seem to make their own or take the same type of technology and brand it with their brand. And of course, you can have moisture meters in bale chambers. And I want to talk about this particular type of tester for just 1 second, or just 1 minute anyway, because In 2019, when it was apparent that moisture content was so important, we secured one of these moisture testers. We bought it and then tested moisture from the bales that we sampled and sent off to the lab. And what we found is that these moisture testers, although they are not simple to use, they did provide an accurate number of moisture content in bales. But of course, you've already got to make a bale in order to test it in this way. So as I begin to summarize this, I want to talk about the correlation of those good farmer practices to good baleage. So on the yes side, cutting early. Absolutely, so it'll have enough carbohydrate in the bale to ferment. Tight and uniform bales are also important. Mowing what can be wrapped in a day so that you don't have excessive heating in the bales before you get them wrapped. Moisture content between 50 and 60%, and even a little higher, probably is going to be acceptable, but certainly on the wetter side of the range to get lactic acid numbers up close to 3%. But I should have put an asterisk here and said that if you wind up with moisture contents below that, and it's not hard to do. I mean, it's when the drying conditions get good, then the moisture content begins to drop rapidly. Just make sure you use 6 layers of plastic and keep the plastic intact. So all of those practices correlate to good baleage. Things we don't know but would like to know. Do you have to have a mower conditioner? We can't say yes or no based on the samples that we have, although we know that when you crush stems of plants like alfalfa or the summer annuals like pearl millet or sorghum Sudan, you make it much easier for the sugars to ferment that are on the inside of those stems. It's not clear whether we have to have a silage baler or not, but it is clear that you got to have a heavyweight baler. It's got to be able to handle the wet material. We did have a few users, or a few farmers that have had and used the knives in the bale chambers, but we can't prove that using knives is necessarily going to lead to better baleage based on these samples. However, it is absolutely true that when you use a baler that has cutting knives and you cut the samples, you engage the knives, that you will make denser bales, and denser bales are proven to ferment better. Rake type will matter, and most of our producers used the wheel rakes that have to have a certain amount of down pressure to move the forage. We didn't have a very large group at all that had the rolling basket or the rotating bar type rakes. Certainly those can be adjusted so they will not engage the soil as much. And one thing we completely were not able to test, and that is, would the application or use of a silage inoculant help our results? We did find that testing of baleage is essential. In other words, we need to know the forage quality in particular because it will tell you the moisture content, and doing a forage quality test is the one place that we got ash, at least from the commercial lab that we used, and we need to know that ash number. We also need to know a fermentation panel, at least on a few bales of yours, so that you can know what the pH winds up being finally, and also the concentration of volatile fatty acids. And while we're talking about testing, it is important to realize that the fermentation process takes about a month. So if you're going to test your baleage for fermentation, then wait a month after baling before you do that. And last, a fermentation panel is going to tell us how much of the nitrogen percent is ammonia. So if you want to create a list of things, of indicators that indicate an increased risk for feeding problems with baleage, it would be moisture contents above 70%, loose, uneven bales, less than 4 layers of plastic or holes in plastic, a bad odor in the bale yard, pHs above 5, especially for those wet baleage samples or bales of baleage, low lactic acid numbers, and here I just say less than 1%, high elevated butyric acid numbers of greater than 0.3%, and a percent nitrogen as ammonia above 15%, and high ash content. And let's just be clear that just one of these, if you've got one of these and not the others, it doesn't mean you're going to have a problem. But the more of these that you have in your baleage, then the greater the indication that you may have a problem. So this brings me to the conclusion of this presentation on baleage. And I hope that we've been able to help you understand how to make good baleage, and if, even more importantly, how to avoid making poor baleage. Thank you very much.